off my camera, so just because it might be the connection might be faster that way.
Okay.
So I'll start the presentation, and today basically I will talk about what I have been doing for the last 12 or so years since I finished my PhD. If there's anything wrong with the sound or the image, you just tell me so that I don't continue talking in vain. So yes, I mean, after my PhD, in finishing my PhD in 2011, I found this company called Programming Architecture, and since then we've been working on a lot of projects, basically dealing with automation. I will not show you too many projects right now. Part of the reason is that because we don't have so much time. Part of the reason is that I can't reveal too many projects, but I will show you some of the main lessons I learned and some of the basic principles I got to extract from these last 10 years, and which are helping me to basically move into the future, to decide the direction where to move. And there are many terms when we talk about what we do. There is computational design, parametric design, algorithmic architecture, and so on. You might find some others, but in my mind, it's all automation. So in my mind, we're not doing anything special or anything that new. We are just automating the thing we're doing since the beginning of evolution. Evolution is basically just a sequence of automating stuff so that we can do things faster and more efficient. And at the end of the day, automation has to pay off. That's how it progresses in the evolution, and that's how it evolves. So what we do, as you will hopefully see, does pay off in our industry, and I'll demonstrate some of the ways in which it does. So in order to basically give you some principles of how we approach automation in our industry and our concepts, I will show you this graph, which supposed to demonstrate that we see everything as a function. So whenever we discuss about some project or whatever needs to be done about that project, we discuss about what the input is, so what the client is going to give us, and then what is exactly in the middle. What are we automating in order to produce a particular output? As a very, very basic example, this is a slide from my PhD, already 13 years old now, that shows that if you take a simple input like a grid structure on the left, and you say, okay, my task is to optimize this, so as an output I get a better structure, more optimized structure that costs me less, is lighter, and so on and so on. That is an example of that function. And in my PhD, for example, I did these kinds of optimizations, and then I showed that with the same number of structural profiles, with the same exact shape of the free-form roof, we can get 3 times less displacement in the structure, 1/2 of the stresses in the steel profiles, just by doing geometrical optimization of the grid. So that was an example of a little bit of theoretical work of how the automation works, but automation is not only about optimization. There's lots of parts of it. So during my PhD, I worked on this airport, which was designed by Massimiliano Fuchsas in Shenzhen, in China. And there, everything had to be done parametrically, right? We had the programming because it was a free-form shape, a lot of unique elements, and no one could do that manually. And there was certain complexity involved, 300,000 square meters of free-form surfaces. We had these hexagonal panels, which were relatively complicated and relatively big. So one of these hexagons were like 4.5 meters wide and 3 meters tall. And there were some additional constraints. For example, the glass surface on the outside. We had hexagonal panels on the inside of the airport, as you can see here, and on the outside. And the glass surfaces on the outside had to be always flat, which is a challenge because you're populating a 3D complex shape over a freeform surface. And additionally, we had like 20 types of these hexagons for which Fuchs literally painted on a canvas where which type should go. We transformed that canvas into Excel tables and then into an algorithm and so on and so on. Of course, working on this project was a long thing. I could do a lecture, 2-hour lecture just about that. But I want to come back to that question, does automation pay off? And yes, it pays off because for the entire airport, we did a complete regeneration of all the facade elements, of all the structure. Remember that this steel structure in between that you see, it was also generated parametrically. So we did every week for more than a year. I think we had 72 generations. We regenerated all these facade elements and entire structure completely from zero, which it took just a couple of hours to do. And that shows the power of automation and answers the question, does it pay off? And not to mention that the entire programming was done single-handedly by me, so which is at that moment, just the programming part, which showed again the power of the automation. And there is a lot of talk of like what this parametric design actually is. So I made a video on my YouTube channel a while ago, and I tried to reiterate this, that's the parametric design as we know it from the internet is actually rarely used. What I mean by that is that we don't use programming, at least in my company, we don't use programming in the first phase of the architectural design, so in the actual design of the building. We do that sometimes. Sometimes we do parametrically design. This is a very old example where we actually had to write some algorithms to explore some design solutions for the structure and so on. This is very early on. This is, I think, even 2011 or 12. But I show this example to accentuate that we do this almost never. So we do programming after the design is done in order to help actually build the project. That's why I write that this is very rare and that we almost never work with architects, which is the sad truth, and that I hope in the future we will do more. But until the end of the lecture, you will see my view on it, and you will understand why we don't work with them that much. So the question is, who do we work with then, if not with architects? Well, as you know, each project has a lot of phases from the design until it actually gets built. And some of them are just static analysis, MEP, HVAC, production. When I say production, I mean the actual production of different elements, steel elements, columns, beams, and so on and so on. So there is a lot of stages, and we usually come at a later stage after the design is over and try to automate everything until the very construction site, even some things at the construction site. So we try to create these bridges, and you will see in what manner we try to do that. But that's our job. And as I said, we rarely do the design phase. So one early example, also from 2013, are these Apple stairs. We did a study because for Apple stairs, they did a lot of these models, Apple Store stairs, where they make these completely glass stairs, but the problem was always that they had to do geometrical models and statical models in parallel, and they were always different because the dimensions changed a little bit. So we made this parametric model where not only the geometry is generated automatically, but the statical model is generated at once. So we kind of wiped out the 8 or 9 weeks they needed to build a statical model from scratch every time a new stair design came in. So that was kind of an automation where we automated the static analysis, so the building of the static model, which is, if you remember this first slide, the problem is that our industry is siloed. So which means when someone designs something, they give it to the structural engineer, they start building their model from scratch, and so on and so on. So we try to create this bridge by automatically creating a design model and a static analysis model. Of course, our tasks range. I wrote here sometimes humans make mistakes. I'm not going to bore you with the details, but we worked on this project where this entire facade of the CAPSARC Research Center in Saudi Arabia was already done and modeled, but they, because of the process of how they did it, they couldn't know for sure if all the elements are right. All these elements, they had them in 2D at some coordinate system plane, but they didn't have them anymore in 3D. So they didn't know if they actually produced them, if they're going to fit back into 3D. So we, for example, made algorithms that automatically read these thousands and thousands of files, with these step files with these panels, and then had to smartly recognize where each panel fits in the 3D and then push it in the 3D and so on. And we found a lot of mistakes, actually. A lot of panels had to be reproduced, but we saved a lot of money by saving them, finding those errors at the construction site. And when it comes to programming, most of the time we don't program just the things that we know how should be done. We just need to automate them to do it faster. But we have to program something to answer questions that to which we don't know the answer. Some of these questions came out in this Schuko parametric facade system, for example, that we did together with Engelsmann Peters. And the problem was that Schuko developed this parametric facade system where the architects could choose a type of the facade element. This triangle here is a one type. This here that you see is a different type. And every type has some points. In this case, these 2 points here, which architects can freely vary. That means that architects can take these 2 points and move them around for every facade element, and the facade could still be produced at a fairly low cost. But then the question arose of static analysis, like how do we know where can the architects move those points, what profiles do we need, and so on. So what we had to do is basically we had to create algorithms that would test different kind of shapes. We would generate literally hundreds of thousands of shapes like this, and automatically do the static analysis for them, a very complex static analysis. And then we would create green clouds of points where the architects can move, or we would give them different types of clouds for different types of aluminum profiles so that they can choose what they do. And those static analyses were fairly complex. They weren't just simple 5-member, 6-member models. They had 10,000, 50,000 members, and everything was done automatically. So this statical model and that geometrical model, we generated like 100,000 of them and tested them statically within hours. So that was the power of automation. A similar thing we did for this Chadstone Mall in Melbourne, where we had a lot of these glass panels, all unique because it was a free-form shape. And then we found out that the standard method to calculate the static analysis of a glass and then determine the thickness of the glass and so on was to approximately choose 4 or 5 glass elements that are considered to be worst case, and then do a static analysis for them, and then apply that result to all the glass panels. And we said, okay, why don't we make an algorithm that just tests statically all 3,300 panels? So we did that, and we tested them within a few hours, and then we found the actual worst cases, so we didn't have to approximate them, and we could also make glass thinner at some panels and so on if needed. So those were some of the examples where we got some input and some output out of the automation. But the question is, for us, is always how much can we stretch this box? Like how simple can the input be, and how complicated can the output be? So that we automate everything in the middle. So on that road, try to automate a lot of production elements. This is an example of a Bloomberg building designed by Foster in London, and inside of this atrium here, there is some stairs and so on, which relatively complex elements. And there's 6 floors of this in this atrium, where for different reasons there was lots of steel elements, these yellow things and red things that you see here that actually hold the glass balustrades. And for those different reasons, because there was a lots of different structure coming from all sides, all these elements are unique. It's nothing, there is no copy paste, there is no repetition here. And as an input, we got literally one curve. So one curve as an input and a PDF, 20 or 30, 40 page PDF with rules saying, if there is something here, then there is a hole. If there is something here, then there is this. Literally 40 pages of if then. So we programmed all that, and then automatically with a single curve as an input and a lot of rules, we generated all these elements, all these red and yellow elements. And there was zero tolerance. We generated them with basically less than 0.1 millimeter precision. And we didn't generate only 3D, we generated also 2D drawings just to check on the site, but also all the CNC files for cutting. So everything automated. And these drawings like this, as you can see, with all these measurements, everything here was generated automatically. So nothing on this drawing was drawn by a human. I am really against 2D in general, as you will see in a while, but sometimes we had to do this. We try not to do this anymore, but if needed, that can be automated as well. On the Kuwait airport by Foster and partners, we did a lot of automation as well. It's a very high span concrete shell with steel structure, so it was a very big structure. And as an input, we also got like simple surfaces and some rules. And as you can see, these are very high numbers. So these curves here, like almost 500,000 curves, basically represent steel members, and in between those steel members was the concrete. And we actually had to generate the entire rebar for the concrete. So the entire reinforcement for the concrete elements with a lot of rules and a lot of automation. The inputs were fairly simple, as I said, just some surfaces and some outlines. So BIM in itself is also automation. BIM is an attempt of automating the tasks that we used to do before. So before, you used to just draw in 2D, and we used to transform that into a 3D building on the site. BIM tried to automate that by letting us create a 3D model and then automatically create sections and plans and bill of quantities for us and so on. And then the reason why I say here that this is not good enough, for me at least, is because we have this weird thing of creating very complex 3D models, translating them into 2D drawings, and then translating those 2D drawings into a 3D model. So from my point of view, this middle part has to disappear, and that's why this 2D has to disappear from BIM. And we are moving toward the 3D to 3D kind of process where we really try not to use any 2D drawings because we find them confusing and not helpful at all. I did make a video about it recently on my YouTube channel where I talk about it in more detail. And but as I said, we don't just talk the talk, we walk the walk. In a sense, there is a project we work on right now, and unfortunately, because this is a public lecture, I cannot show anything about it. But it's a very high profile, extremely big project. It cost $2 billion. And in this project, it has an enormous steel structure. And on that steel structure, it has a secondary aluminum structure, tertiary aluminum structure, then it has some LED screens on it, and so on and so on. So it's very highly complex, but we do not use 2D at all. So we generate a structural and production model simultaneously. So the civil engineers don't have to do anything, don't have to do any modeling. They just get complete models from us, and just have to press calculate, analyze. And there is a lot of structural members. As I said, more than 30,000, more than 90 million works. Work is a term we use for the G code for the machine, because for every profile that we make, which is all of these 30,000, they're unique for different reasons. we automatically create G code. So every drill here on this profile here, every cut, every mill is a work. So there's like more than 90 million works that are automatically generated, and all of these profiles are then mass produced in a machine, and they're stamped so that the workers at the construction site know how to install them, and all of this without any middleman. So everything automated, from a couple of simple rules until the done files, STP files, G code files, everything goes into the machine and goes directly to the construction site afterwards. So all of this for this $2 billion project and very large scale, 120 meters in diameter, we did those all in a team of 2 or 3 people. We do not use any 2D, do not produce any 2D, any cross sections, any drawings of structural members, nothing. It's all 3D and directly G code. And a bit more interesting maybe for people that are from the industry, that we did not use any BIM software. So it was all done in Rhino using programming. All the attributes were there. Everything was, we were able to extract and to generate everything with the code. And the question for this, for me at least, is long-term thinking. So where are we potentially going with this? So trying to automate everything and trying to stretch this box. Well, I think that the general direction is AI, and I'm sure we're gonna hear much more about it in the next lecture. But I made a video a while ago talking about, can AI out-design architects? And that's a relatively interesting question, especially because if you look at the process of the building development, I see it as in these 3 main phases: as design, development, and actual building, so the actual construction site. And we are mostly, my company, we are here in the middle. We basically try to automate everything here that comes in between the design and the construction site. And there is some semi-automation at the construction site. Of course, we have robots, we have different construction machines that are all considered a part of automation. But I think this will be fully automated when we have either 3D printed buildings, or we have robots that actually assemble all the elements that we automatically generated. I'm not going to enter between those in the competition between those two, because we in our company actually work on both things. We're doing some research project on 3D printing, and we're doing some thinking about how this automated assemblement on the site could work. But that's the construction site itself is a story in itself. The design phase is something for us that's very open, because as I told you, we did not work much on the design phase, and we consider the parametric design done in the design phase not yet at the level that it should be, and that it's maybe waiting for an actual AI designer. But for me, can AI out-design architects is kind of the wrong question, because I don't think AI is there to replace architects anytime soon. And I'm a firm believer of pen and paper being here to stay, because AI could maybe be programmed to design something for AI, but we can hardly program AI to design for us, because we do not yet understand what is pretty and what are our needs. We kind of do it instinctually. So in the development of AI, we had a lot of these famous events and steps. But for me, the interesting thing was that after chess being played human versus human for such a long time, and then being played human versus machine, where machine finally in the 90s took over, and now no human can compete with any machine when it comes to chess or even Go. The interesting thing for me to learn was that a human a machine team, so a human together with the AI, could still beat the AI. And that's something when it comes to chess and similar games. And that's something for me, that's how I see our design industry, AI being the advisor, so human-machine team working together. And in this small example where I envisioned how it would look like, it was for some research proposal years ago, I just made a little story here where a user would put some supports for a bridge, and then the AI would suggest, and then that's why I emphasize here, suggest is the key word about some shapes. Then the user would pick some, then AI would maybe suggest some structural volume, then the user would adjust it or fix it. Then AI would maybe optimize a structure over that structural volume. And then again, the user would be able to choose some of them, adjust some of them, pick some of them, and then they would basically continue on this process and refining the model until they came to a solution. So what they would be doing, they would be playing, they would be playing purposefully, in the sense that the design exploration by the user could be controlled, not necessarily controlled in a bad way, but helped with by the algorithms. And we should use the tools that are already here. That's the point that I'm always trying to emphasize. I think Buckminster Fuller and many others have noticed that the construction industry lags behind other industries, and that we usually need 40, 50 years to start using the tools that are already used in other industries, like robots are used like this, are used in the car industry since the 60s, 70s, and we just started using them 10, 15 years ago. So we should, there are lots of tools that are already here. We just have to use them. And I am a firm believer that by using the tools that we have, not only hardware tools, but especially software tools, which is my expertise, we could build a building like this for the same amount of money that we need to build a building like this. Because at the end of the day, machine doesn't care if all the elements are different or the elements are the same. So in this, if you imagine printing this in 3D or printing this in 3D, the printer would not complain. They would just print this, use the same amount of material. In the same way, I firmly believe we can build buildings like this for the same amount of money as this, just with the smart programming and automation. And because the design itself is a selection of ideas, I think when we design, we do not have time. So we can test 4, 5, 6 ideas, but then we do not have time to test more. And automation can help us merge and come up with some different solutions, merge ideas, and then basically automate this process, whereby we could test as many ideas as we can in the beginning, and then come out with more creative solutions. So I think I'm exactly almost at the half an hour mark, and 2 more minutes, and I will finish with this inspiration that I always had when I went to Japan and visited some small village in the Shikoku Island. And they told us in the village that there is a speaker temple in the village, and we had no idea what they're talking about, because those two words could not be combined together for me. Speakers are something that when you listen to music to, and the temple, we know what the temple is, and the temple symbol in Japan. And then we went there and we saw something like this, and this always reminds me of the creativity we have in us. But it also always, when I look at this picture, it reminds me how complex it was to actually build this, and how much time it took to test and see if this works. So this is, for me, this picture for me, a symbol of something, of the creativity we as humans can produce, but also as something where automation itself could help us build if we just employed the tools properly. So yes, thank you very much. If there is any time for Q&A or desire for Q&A, we can do it now, but that was all from me. Thanks again.
All right, thanks, Milo. Let me see. If you have any question, you can type in the chat now, or you can type anytime, and then we can address it at the end of the 3 talks as well. Anyone has any question? Okay, I don't see any question. Maybe can I just ask one question?
Sure, sure.
Yeah, you talk about the working relationship with the architects, but can I know more about your working relationship with the contractor? Because the design and the form are rather complex, and you mentioned when you produce the drawings from 3D to 3D without any 2D drawings. So how do you work with the contractor in that respect?
Well, I mean, the contractor itself has to be advanced, right? So we are lucky to work with some companies that are fairly advanced in the field. So they actually do not ask us for 2D. The only time they do ask us for 2D is when they outsource some of the work, and then that outsourced company asks for 2D. And it's usually something relatively simple, just like some installation plan, so that when the construction workers go to the site, they know which element goes where. Those things can be automated as well. We do prefer to go to the construction site with the iPads, or with the 3D models and so on.
Oh.
But that is still a slow process. So for a lot of projects, we do still have to provide some kind of paper that's been taken to the construction site, especially with a big project like this. But yes, it depends on the contractor. We had not a bad experience, but we have some contractors who are very old school. Yeah. And in those cases, we do produce 2D drawings, but we produce them automatically. So it is an additional effort, but at least we do not have to sit and draw them manually. We produce them automatically.
Okay. Yeah. So do you think it's a matter of waiting for the construction industry to catch up before this method of working? Yeah.
Yes, because it's as I said, automation is evolution. It's more efficient. It's more efficient and it's more precise. There is much less human error. That's the biggest problem. There's a lot of human error when it comes to manual drawing, and there's lots of human error and error at the construction site. So this, by doing it in 3D to 3D, just having one centralized model, so where everybody can chime in and check stuff, that makes stuff much more easy.
All right, thanks. Let me see. Okay, we have no question coming in yet. So if you have question, you can type in the chat as mentioned. Maybe I can proceed with the next speaker and see whether Professor Immanuel KOH has something to say about whether AI can out-design architects. Immanuel, maybe you can take over and share your screen.
Right, thanks. Yeah, let me share my screen. All right, is it in presentation mode? Are you able to see the first slide? Yeah, okay, right, good. Right, so thanks for the invitation and also the quick introduction just now. So I'm an assistant professor at the Architecture and Sustainable Design program, and also the very new program called Design AI program at SUTD. So it is also where I direct my research lab called Artificial Architecture, and it is also where I teach design courses to architects and students from the computer science, the new program, meaning deep learning and machine learning. I'm also the co-founder for the collective called Neural Architecture Group that curates the AIarchitects.org online platform. If you are free, you can check it out. I previously worked in Zaha the Architects, although not that project. And I did my PhD at EPFL, École Polytechnique de Fédérale de Lausanne in Switzerland a few years ago, about 3 years ago. And I'm very happy that today I could get this opportunity to share with you my perspective on the topic of AI and for architecture design. So most of the projects that we'll show will be kind of focusing on the more generative aspect of it, more experimental, more speculative, rather than the other more serious work. Serious meaning can be quite boring, so I'm not showing that many of them. So these are some of the kind of work that I do. So some topics that I've been looking at in recent years. So if you look at the kind of work that I do, it's kind of a spectrum in kind of more art and design scenario, where exhibition and event is architecture biennale, and also even book design, which won the Golden Pin Award just last year, and also a bit more serious projects that appears in conferences such as the International Conference on Computer Vision, ICCV, quite a high profile AI conference, and other more neural architecture related projects like this one. And of course, NeurIPS, which is also quite a high profile AI conference. The industry project would be those that I currently, those include the one from URA, the MINDEF, and also the resource support from the National Supercomputing Center in Singapore. Yep. So for those who are curious about more recent writing, apart from projects, of course, some projects will actually appear in these publications. You might want to check out some of these. These are very recent. Half of them from just this year, early this year. So the first one, for instance, this one is the book that I wrote, which kind of, it was an introductory book for the school, for SUTD, because it was a new course on AI and architecture theory. So you could get it online. These are some chapters that I contributed, such as the AI and architecture from research to practice. So I think you could access it from your library. Right, so some glimpse of the architecture design issue for the discrete. That one was quite some time, but nonetheless, it is related to the early work in machine learning. More recent one, for instance, this one that you saw in the animation from the AD machine hallucination. Not so much about automation in this case. In fact, I wrote something about the necessary fallibility of the system for it to go beyond the automation. And also this one, the idea of architectural plasticity in relation to 3D generation. And also recent project, those who are in Singapore, we have seen the exhibition at the Arts House just a month or so ago. And also some projects exhibited elsewhere in Australia and Venice, and recent NFTs released from AI-generated furnitures. So now returning to our lecture proper, let's look at the lecture title again. Clearly very straightforward. Artificial intelligence for architecture design, which is basically the use and application of AI models for the design of architecture. Or in very simple terms, architecture design being the creation and composition of interrelated forms and spaces, typically manifesting themselves as physical buildings. Interestingly enough, if we were to flip that order of the order of both terms and change the preposition between them, or you could read it like this: architecture design of artificial intelligence. That is, designing the architecture of AI models. So in accordance to our common understanding, contemporary understanding of what contemporary AI models, they are, is referring to deep neural network models. So AI models are commonly understood as deep neural network models in the contemporary sense. And therefore, architectural design here would then mean in simple terms again, the creation and composition of interconnected computational neuronal units or neural layers as a deep learning model, typically manifesting themselves as virtual intelligence. Right, to avoid this possible confusion about the phrase architectural design, I decided to add a superscript to each of them. So where architecture design in the first sense refers to the architecture design of intelligence, because we're in fact designing the model, the AI model itself, while the second sense refers to architecture design as the design of buildings. So in other words, working with AI and architecture today will in fact engender two orders of architectural design. Maybe a useful, though actually not accurate, analogy would be for those who are familiar with composing a grasshopper definition on Rhino, which is essentially an acyclic graph, directed graph on Rhino. You can imagine this is kind of a first order of architectural design as at the meta level, but it is truly inaccurate as an analogy because deep learning models in AI are not only defined by their structure, their architecture, their graph representation, but also by the actual process of training, meaning the kind of data set that is being fed to the model, and also the training process itself, which in fact involves millions of parameters. One project that I was recently presented for a funded project, that we created a few iterations of the same neural network architecture, but changing the intermediate layers, and we were getting like 40 million parameters to train. So diagrammatically, before I move on to the more interesting, visually interesting projects, diagrammatically, this is what we get. So the proposition here is that the architect is for the architect is to gain, if he is to gain true design agency, he or she should not only use, but in fact, also design the architecture of the AI model. And in fact, creating this sort of iterative process or feedback loop between the architecture product, meaning the building, and the intelligent process. So let me show some examples. Usually this is quite a kind of easy entry for those who are unfamiliar with AI models, because it is an example of a very simple book that was recently produced at SUTD, and which won the Golden Pin Design Award for its innovative use of AI for book design. So essentially what we're seeing here is every single cover is different, and there are 700 of them curated from theoretically infinite number of versions, and is generated by this AI model called the Deep General Adversarial Network, or simply or the acronym GAN itself, GAN, with a training set consisting of visual archives from previous years of student architecture work from SUTD, which since 2017 in this particular case. So the design concept then is to ask the AI model to generalize from what it's seeing from the archives, and then ask the model to learn these, to unearth these latent features, and then generate, once it could generalize, could generate similar versions that is representative of what it has seen, meaning the training set. So usually when we talk about generative design, or in this case, designing an image, a cover, we would either manually manipulate pixels or compose shapes on Adobe Photoshop or Illustrator, or we would write a very kind of highly specific code to procedurally generate, maybe with like lots of if statement, to generate a limited range of cover design. So what we're seeing here on the right side is I drew it so that it becomes easier for designers to understand. It is the architecture visually made simple of the neural network that been used for training that model. So if you look closely, we can go into that later on in the Q&A if you want. So this is a quick video. So here we're looking at the training set. Simply just images. Of course, in this case, cutting them up so that we increase the number of data points, meaning the size of the data set, and then using a style again to kind of train the model. And then train again. After evaluating the output and the performance of the model. So this is the process where the human comes in the sense that he or she would change the training set, improve it, or change the neural network architecture, or change the hyperparameters, things like learning rate. And so here, for instance, because it was kind of trained and generated with a low-res imagery, and you need this additional AI model to do a super resolution process so that it's suitable for printing at the very high resolution. So in the book, there are 4 pages or so to explain the whole process. So if you are curious, you can also get the book. Okay, so in fact, today I'll show 2 main forms of sampling. I usually use the word sampling because it is actually taken from my PhD, which is called architecture sampling. But essentially based on many of the projects I will show based on 2 main families of AI architecture models. On the one hand, you have the AI architecture design. So designing of the architecture of the AI model, which is closer to what I showed you just now, the GAN models, the variational autoencoder models, where you ask the model to learn a continuous space of representation of what it's saying, and then you sample it and generate the output at one go. On the other hand, there are models, in fact, there are many, but these are 2 of the ones that I really like. The one on the right, which is based on a different way of working, that it generates as a sequence, discrete sequence. So it learns the distribution as a sequence, and then it generates one at a time. I'll show you an example, like the NFTs that I would show you just now. It's based on this sequential way of modeling. So the first one, yep, this is way more simplified than the one I show you, just because it's easier to have. A quick example, just so that you could slowly understand what the kind of work that I'm doing. So this is an example where we know that in 2020, the Serpentine Pavilion was not actually built because it was postponed due to the pandemic. So the idea of this project is to learn from a training set of previous 20 years of pavilion design. It's interesting also in this case because the site is exactly the same. The budget is similar, and many things are very similar. So it seems to make sense to train, just like the book we have just now that I showed you. We do something similar for the Serpentine Pavilion 2020. So again, this is that continuous space of exploration where we sample from that space, latent space that the model has learned, and it generates. So what we're seeing here is not frames in a video. What it is, but it is actually moving in that very high dimensional space with many parameters. And therefore, here we could see sometimes you see features of some designed by some architects. Let's say here, So Fujimoto on the left, and then sometimes you see Peter Zumthor's, and so it's kind of doing what was intended, right? To learn what has been kind of built previously in 20 years and see how we could sort of remix them in interesting ways. In fact, during this process, there was a need to balance the data set. Apparently, during the data scraping, there were too many images of So Fujimoto's pavilion, probably because it's very popular, relatively speaking. And therefore, there's a need to do so, which means that we could also control the performance or the generativity of the AI model sometimes just simply based on the data set itself. if you could curate it creatively. Let's move on. So these are some examples of the generated output. But to go one step further is to ask another AI model, to train another AI model, say, given one of these images, can you tell me what's the proportion of that image looking more like a Gehry picture or a Zaha design or a Sou Fujimoto or Ito building? So in this case, what we're seeing here is these are the percentages. So the rows represent the different generated images from our AI model, and it's showing the percentages of fidelity to or resemblance to what the model has learned, what is considered more Frank Gehry or less Zaha. So to represent it more visually is that, for instance, in let's say this image, number index 36, the AI model, in this case, not the generative model, but the predictive model, thinks that 53% of it looks more like a Zaha and 46% of it looks more like a Ito. So then the question is, if we want to measure the interestingness of an output by a model, what might be a nice golden proportion, right? Kind of, is it more, 30% of one architect and 60% of another architect, or something else? So I think it's interesting also because the AI becomes a kind of a reflection of the ways in which you could think about our design process and the way we perceive and judge design. So let me move more quickly, the more three-dimensional. So bringing you really back into a more three-dimensional representation of AI models. So we've gone through, this is a quick video so you can have an understanding, and I will look at snippets of the video later on in the subsequent slides. So what we're seeing here now, instead of these morphing images, we have these morphing 3D models in high resolution, where ideas of circulation, vertical circulation, corridor connections with high-rise apartments are being learned. And so here is the exterior and the interpolation. And this is the section that we cut from the output. So rather than generating an image, now we're generating an entire building block, which you saw just now in the interior cut, the section cut on the first slide of the presentation just now. So this is kind of a zoom out view of it. We see that it's behaving correctly in the sense that the understanding of what's constitute a workable high-rise building is that it has the right length of corridor that is connected to the vertical core, the staircases, the lift core connected to the apartments, and it shouldn't be too thick, too thin. This is an example of clustering, actually a UMAP. These are the data sets, and the numbers at the bottom, the two numbers, represent the geolocation, that long. And these are real buildings, in the sense that these buildings exist in Singapore, and these are high-rise buildings. And so here, just like what we learn from image, we can also learn from 3D models. Just like we train the image, here we see the training is trying to converge. As you move towards the end of that sequence just now, you see it's becoming more like the building because it's converging with greater confidence. So these are two different AI models, different in the sense that they have been trained differently and there are differences in the hyperparameters. The one on the left represent seemingly more workable meshing. I simplify it just so that it's easier to understand. On the right is suffering from the lack of confidence in the sense that every voxel is not very sure because they are less black, more whitish. In this case, is visualized as being less confident of their position in that space. Therefore, yes. So therefore, we could see that AI models are actually, deep neural networks are actually kind of alive because every time you train it, it will be different. So even if the same number of runs, the same architecture, the same hyperparameters, they will be different. This is an example of if you even to mix different kind of training set, let's say in the case of a chair and a building block, what do we get? Is there might be the kind of an in-between, just like maybe what Melo mentioned about the speaker, is it a speaker gate? So what's a chair building, for instance? And that kind of push that the conceptual constraint that we may have about things. Just some images. So in this case, this particular model has been trained for 2050 epochs. I'm just showing the interpolation and the zoom in of these. They are very high res. For the interpolation, 2050 epochs. I think I should move quicker. And so again, a snapshot of what it means from the first. So when we talk about epoch, it's like in an evolutionary sense, that the model is evolving in its understanding of what it's seeing. I won't use the word understanding, but accuracy in approximating what it's seeing and what it's producing. So as we move to the 75 epochs, in the 75th generation onwards, it's becoming more building-like. In the beginning, it's kind of this blobby object that makes no sense. Apartments are over, whereas over here we see staircases appearing. Okay, so again, zoom in into the example where we could deliberately ask a toddler AI model to generate something that is less correct, but interesting enough, but slightly incorrect. So here I'm showing a less matured model that generates something that looks like a building, but quite messed up because the top part is a mess. And as it gets older, 5 years at a time, it starts to understand circulation and apartment distribution. Of course, in this case, it's very unusual because when we do high-rise design, we would never be so generous enough to have most part of the building to be circulation spaces, communal spaces. But instead, we would want to increase the floor area for the sellable areas. So again, the AI is kind of pushing what we are comfortable with typically. PK, do I have, how much time do I have left?
You can continue for, let's say, about 5 minutes.
Okay, right. Thanks.
Yep.
Okay, so the same project has been exhibited physically because actually physical models were made. This was the exhibition. This exhibition is interesting simply because it's an exhibition with Ong Kim Seng, who is a cultural Medallion artist, watercolorist, and the project is really to kind of show this simple narrative of human, not exactly human versus machine, but the creative process between two modes of working. So on the left would be the AI, which the kind of work that I did. I showed you just now on the right side, the watercolors. Some examples. So what we're seeing here is the 3D printed version of the interpolation at the scale of 1:300. This is 1:100, a fragment of a block. Some zoom in of the parts, and very quickly the discrete sequence. So here, this NFT that was released some time ago is actually for a charitable organization, which has to do with the idea of abuse and the underprivileged, and therefore there is this deliberate kind of intention to create these chairs that look inviting and uninviting, strange and yet familiar. Therefore, and kind of an artistic undertone to it. So these are actually available to be purchased. I'm not asking to buy it, but showing examples that how to kind of move AI generated artifacts into that kind of a blockchain scenario. This is a quick process of, on the right, it's just an example of the data sets that is being used to generate the furniture on the left. And here what we're seeing is that it's learning the distribution of the vertices and the faces. And although we're seeing that they are generated one at the entire object at one go, in fact, it's generating one vertex at a time, and then creating faces after that, one face at a time also. These are 3D NFTs that is also AR ready. Yeah, last project will be this. Those who are students of architecture will be very familiar with the Barcelona Pavilion by Ms. van der Roon. So the question is then, can we also use single data to generate variations of it? So in this case, it is quite possible. So around it, in fact, of course, I removed the roof of the Barcelona Pavilion. Surrounding it are the variations of it based on learning just one data set. One data point, in this case, one single model. So again, to rethink about, I probably won't have much time left, but rethink about how to kind of numerically represent a floor plan even. Here is that, in a machinic way of saying, just almost like a convolutional way of saying, is that we're seeing grids, but we can see it at different resolution, 0.05 meters or 2.2 meters or 1.1 meters. These are examples. These are the same discrete set of modules that's able to represent the full Barcelona Pavilion. And with that, we could do so here, for instance, is without machine learning, in the sense that it's just using uniform probability distribution to just generate the parts and put them together. No intelligence, in the sense that at least it doesn't have a sense of probability distribution in the right way. And in this case, just looking at the frequency count of the training set. But we can begin to tweak the model so that it becomes biased towards a certain formal preference. Here, the horizontality, the verticality, in this case, much more controlled, in the sense that it's considering a larger neighborhood in its generation. So I think I'll skip this part because we're at the end of the lecture, but this quick video to show you, this is the last project. I thought it's fun because usually students, those who are quite anti-digital, they would prefer to see. This is actually the one on the right is generated by AI model trained on sketches. So the idea is using AI to not to extract, but in fact, when artists draw something, he's abstracting. So you could check the text. It's over at the bottom. It's called artificial. It's under the artificial creativity publication under transformation. Yep, I'm done. I think I have gone too long.
No worries. Thanks a lot. Very interesting talk. I don't think questions are coming in yet. So perhaps I will move on to the last set of speakers, and then we can come back to the Q&A. All right?
Sure.
All right.
Right. So for those who have any question, you can just continue to type in the chat. And so lastly, we have two speakers with us, Christoph Zechmeister and Hans-Jakob Wagner. Maybe you can take over and share your screen.
Sure.
I pronounced the name correctly.
No, that was perfect. Yeah, so hi. We're Christoph Zechmeister, that's here, and I'm Hans-Jakob Wagner. We're also super happy to be here today and present you our work that we are conducting at the University of Stuttgart. More specifically, we're both at the ICD, that's the Institute for Computational Design and Construction. And we'll try to keep this rather short, but still give you kind of a comprehensive overview of what we're actually doing here. And by that, show you two of the prevalent kind of material systems that we're working with. One will be presented by Christoph, is the carbon and glass fiber structures, and I'll talk about the timber structures that we're working with. So I'll start with the timber part. My name is Hans-Jakob Wagner, as I said.
Sorry, Hans, you're not sharing yet, right?
No, we are actually. You cannot see the screen?
No.
Because
yeah. Maybe
okay,
try.
Let's try again. Yeah.
Is it working now? Can you see the screen?
No, I don't see. Am I the only one? Yeah. It was good.
It says we are sharing, but let's just try again. No? Yeah. That's good.
Can you try to share the other screen?
Window. Try. Still doesn't work, right?
Still doesn't share, right?
No, yeah.
Zu Bedingungen auf dem Server.
Nee, nicht die letzte.
Sorry for that. It's very inconvenient.
No worries. Yeah.
It just worked before. Let's try this.
Ja, weißt du, was wir probieren könnten? Einfach mal den Ding ausmachen.
Mal rausgehen. Ich habe auch die nicht gesehen von den anderen.
If it helps, you can also maybe you can leave and come back. I don't know whether that helps. Yeah, so we'll wait for them to restart. Yeah, meanwhile, is Milos, are you still there? Is Milos there? Okay, sorry for that. Let's wait a couple of minutes for them to restart and join us. Yeah. Hi, Robert.
Hi, PK. Hello, everybody. Maybe we can take this time to welcome our students. Just wondering who are our students in this session. And also, you have any questions regarding the competition that we are organizing. We have some teams that have already registered. So we would like to encourage more teams. And any queries you may have, those who are still planning, thinking, please feel free to email us, ask us. Okay, looks like our two Stuttgart researchers are in.
Yes.
Hello, Christoph and Jacob.
We
Yeah,
can
I
see
start.
now.
Yeah, I
but
can see now.
Your mic is off. Yeah.
Yeah.
Yeah. Your mic is off. You're muted. Yeah.
Okay, sorry for that. Now it should work. I guess you can see the screen now, right?
Yes.
Okay.
Perfect. Sorry for that. So yeah, now with the pictures, we're from the ICD in Stuttgart. Me personally, I'm coming from the Technical University in Vienna. I'm here in Stuttgart since 6 years now. Yeah, my focus is on the computational wood architecture topic in the institute, which goes hand in hand with also the robotic production systems. And when I started here, the ICD was already kind of known for pavilion scale structures that really tried to also materialize the advances in computational design that a lot of them were made already in the 90s and early 2000s. The core innovation here was that arguably the direct link between the digital models and the affordances that you can generate through the computational design methods was directly linked to the digital fabrication, to the robotic fabrication, and therefore opened completely new avenues toward what you can actually build. But then after doing that for a couple of years, of course, the question became stronger and stronger how to bring this to a bigger scale. And this is what I want to present today. So when I started in ICD, I started with the Buga Wood Pavilion, which is arguably still a pavilion, but in terms of the scale, with a 30-meter span and 500 square meter footprint, it really represents the leap of this kind of research into the real building scale for us. As you can imagine, at that scale, and especially it being a public building, it needed to go through all the building regulations and needed to comply with all the codes. But still, we were able to showcase how the direct link between the digital design and the robotic fabrication can be established also with industry partners that we are very happily collaborating with in all of our projects. And then at the end of the presentation, I also want to give a quick outlook on how we believe the same kind of methods and technologies can actually also be transferred to somewhat more regular building projects. But this is, of course, a field where these technologies can really have a big impact on how we can actually make our built environment more affordable and more adaptive, and make it, of course, also more give it a higher spatial quality. All of that in our institute is run under the umbrella framework of co-design, which is kind of widening a bit the horizon of the initial idea of integrative design. So you try to integratively bring together different disciplines, different aspects within the design, rather than starting with an architectural concept and then later trying to figure out how to actually engineer it, and then even later figure out how to build it. In this co-design framework, we tried to bring all the experts and all the disciplines together from the start, and leverage this kind of potential for innovation, as it really kind of represents this comprehensive set of knowledge on the planning table from day one. Then, of course, we're a big reason how that is actually only possible, also in terms of an organizational kind of point of view, is that everyone is working on the same model, and everything in the model is kind of responsive and adaptive through the generative algorithms that run in the background. That means we can very quickly iterate, of course, through a lot of design iterations, and everyone in the team can fairly easily make changes in the model. Then relating to the robotic fabrication, we use all the data that is in this kind of computational models directly as a kind of control architecture for the robotic fabrication. So we kind of jump over the semantic gap between the designer and the fabricator, where a three-dimensional model is kind of collapsed into a two-dimensional plan, and then needs to be interpreted by the fabricator. But rather in this case, we're directly streaming the data from the model directly to the machines, which then know exactly what to do. How that looks is, as an example, is here one of the cassettes that we assembled for the Booger Wood Pavilion. You can see the two robots assembling these cassettes fairly quickly and efficiently. It's fully automated, but it's also automated in the sense that each cassette is unique, actually. So we try to expand the notion of automation with that. These cassettes are then machined also within the robotic platforms. And one aspect that we are always happy to show is that although robotic fabrication technologies are not necessarily discussed as the most precise in the industry, we actually showed that you can work very precisely with these kind of machines to establish interfaces that are working effectively with zero tolerance, and still you can assemble this kind of pieces fairly easily, even though all the pieces have direct contact, which is of course only possible if the assembly accuracy is fairly high. Yeah, with that we constructed the pavilion in 2019. It served as a kind of flexible event space, and you can see also here how the acoustic contraptions, the lights, and the structural design is all kind of embedded within these kind of systematically very simple cassettes, and unfold this simplicity through a very adaptive and performative global shape of the pavilion. Now, if you look into what's happening still in most of the industry applications today, is of course fairly different, and also in the timber construction industry, which is very much the most innovative field within construction. We still see like a very kind of close-minded view on how we are able to build with timber, and this is of course very uncanny, especially in terms of how it relates to the history of architecture, where this kind of idea of modular and standardized and systematized ways of building was very much kind of trendy and pushed forward in the 20th century, in the early and mid years of the 20th century. we know, of course, that a lot of that has dramatically failed, and still, even though we give this kind of idea new words and we embed the same systems in digital frameworks on a very kind of basic level, it's still fairly much the same. And just by it being digital, we kind of don't believe that it's also gonna convey a drastic kind of change in quality. So what we are doing in the ICD is we are really trying to fundamentally rethink and push the technology of timber construction to leverage the same potentials that we can achieve currently with concrete structures, which is basically quasi-monolithic slabs that have multi-directional structural spans. And by doing that, we try to offer new design possibilities to timber structures in multi-story construction. We're currently testing this on a small-scale prototype, which is called the ITEC Campus Lab. It's a fairly simple, as small as possible demonstration of this idea with three columns and two slabs that are spanning in this kind of three directions. They showcase a span of 8 meters, which is fairly decent for a timber structure and a flat ceiling. And this, we hope, might become the new kind of skeleton of a lot of the built environment that we can construct with this kind of technology. With everything being out of wood, there's basically no steel within the connections, and that, of course, could be a big step forwards towards a sustainable built environment. Looking into the future, we're currently also planning a big laboratory building in Stuttgart, where the excellence cluster that we're currently running in will be housed, and we're trying to showcase exactly this kind of idea in that bigger scale. Also raising again the spans from 8 meters to 12 meters, and not only 12 meters in one direction, but effectively 10 to 12 meters both in the strong and in the weak direction of this kind of systems. And with that, we can, of course, afford a fairly flexible architectural structure where you can put interior partition walls throughout the years, always reconfigurable, whereas the main structure can remain as long as the building is standing up. And with that, we hope that we can bring the same kind of qualities that we can achieve today with concrete. We try to achieve the same capacities with timber construction and make them affordable through the automation and the automated design that we develop. Yeah, with that, I would give over to Christoph, who's going to talk about the fiber systems.
Exactly. Thanks, Jakob. My name is Christoph Zechmeister. I'm also a research associate at the ICD. I'm trained as an architect. I used to study in Vienna and in Zurich, and I joined the ICD a couple of years ago in 2018 as part of the research team on fiber composites, which is my main area of research. My PhD is embedded in the Cluster of Excellence in CDC, which is short for Integrative Computational Design and Construction for Architecture. And I'm focusing on the co-design of robotic prefabrication systems and architectural fiber structures. So if we look at how fiber composites are usually created in the industry, it becomes immediately clear that those methods are not very well suited for the construction industry or for architecture. It heavily relies on complex formwork, and producing such a mold is obviously very expensive. It's also very labor expensive. And while this might be feasible for industrial manufacturing of products or for mass production, but the mold can be reused many, many times, this is very problematic in architecture. And looking at the question, why would we even want to build with fiber composites in architecture, we can see that this kind of material has very high potential for the application, especially in large scale and long span structures, if we consider the strength to weight ratio of those materials. So they are very strong and they are very lightweight. And the material we are working with are fiber rovings. So basically those are untwisted parallel fiber strands, and they are anisotropic. So they have different properties in different directions, and we can use this property to our advantage. And we can create controlled anisotropic fiber arrangements and can match the stiffness and the strength of this resulting composite to the direction and the magnitude of the occurring loads in our structure. And that gives us a lot of control about the material amount in specific areas. And it allows us to extensively customize our structures. And that again contributes to a very high material efficiency, which is very important if we consider that construction is one of the most environmentally problematic human activities. And here, being efficient with material expenditure becomes a key factor for sustainability. So how can we leverage the potential of this material? We can do that by also rethinking the way how we can produce such composites. And what ICD has been developing for a few years now is kind of a new type of filament winding and additive manufacturing process, basically, that mitigates most of the formwork, and it only relies on very minimal boundary frames, as you can see in the slide. The fibers span freely in space between those boundary frames, and the hyperboloid shape of the composite emerges only from the interaction between the fibers. And that's at the same time a key component of fibrous form, where we need to think about the composite not as something that is a passive imprint of the mold, but it's rather something that emerges from the complex interrelations of the fibers in space and time during the fabrication process. And this also demands a much higher level of integration of fabrication into design and engineering. So how can such a fabrication setup look like in real life? This we can see here. That's a coreless filament winding setup that we used for one of our projects. There's a 6-axis robot arm, which is the main fabrication agent. It carries an end effector, which guides and deposits the fiber rovings. We have a winding frame, which positions the anchor points in space, and we have the anchor points themselves, which create the interface between the fiber rovings and the winding frame. And this is what such a setup looks like in action. So the robot pulls the impregnated fibers through a tube-like end effector. It hooks it around the anchor points along the frame, and it keeps traveling back and forth between those frames until the composite reaches its desired thickness. So how can we design for this continuous process of formation, where basically we have a non-linear process and we don't really know the end result, like this kind of equilibrium state that the fibers ultimately assume. And here the continuous nature of those fiber filaments demand quite a different design methodology than what we are used to in conventional building systems, where we conventionally combine discrete elements in one way or the other. Here we don't have that. We have this infinite fiber that we somehow need to manage, that we need to organize. And we do that by defining the sequence of the connection points. So basically in which sequence we connect those points. And we call that the fiber syntax. And that kind of gives us the recipe for those components and gives us the means to describe the fiber layout of those components. And this fiber layout, we can split in different layers. We can break it down into this layer configuration, where each layer caters to a specific requirement of the component. And this gives us a very flexible tool to specifically respond to local requirements of the structure. But of course, fabrication and design of the composite component is not everything. That's only part of the bigger picture, and Jakob already touched on that. We also need to consider engineering methods, construction processes, building and material systems at the same time, which is what we call co-design, and which ultimately is what enables us to really exploit the full potential that those composite materials offer to us, and at the same time also use the computational power that we have available today. It also enables us to complete large-scale architectural composite structures on time and on budget. And one of those we can see here. So that's a large-scale, long-span structure that we did in 2019, the Buga Fiber Pavilion, for the Bundesgartenschau in Heilbronn here in Germany. It's a dome structure that has a span of 23 meters and a surface weight of only 7.6 kilometers per square meter. And this low weight is facilitated by the high amount of customization that I just explained before with the layer breakdown, where we have a high degree of adaptivity of each fiber component. So the Buga Fiber Pavilion demonstrates the potential of composite structures for long span applications. But can we also expand this idea of robotically manufactured fiber composites towards an inhabitable multi-story building system? This is what we try to do here. And in this diagram, we can see a modular composite wall and slab building system, which uses a very simple and compact fabrication setup. And if we compare a conventional concrete slab to a corresponding fiber composite part, we will see that obviously with the fiber composite, we can be significantly lighter. And with a concrete slab, or like a conventional concrete slab, we have to accept all kinds of redundancies in favor of mass production, whereas in the fiber slab, we can really focus the material effort on structurally critical areas. In terms of fabrication, that was quite a simple and compact system. We used a 6-axis robot and an additional turntable. The production setup easily fits a standard shipping container with the idea to be later moved on site, act as a mobile factory where it could carry out production, but it could also be used in the future to expand or convert existing structures. The size of the elements is very manageable, so it complies with conventional shipping standards. It can be put on a boat, it can be manhandled with like simple tools such as a pallet truck. And this was the result, a modular multi-story composite slab and wall system that we exhibited at the Venice Architecture Biennale last year. The structure consists of 30 load-bearing fiber components, 20 slabs and 10 walls across 2 floors. And it showcases a new kind of material culture of dematerialization that is based on digital construction method and that leverages the potential of these highly anisotropic materials. Yeah, so far we talked about robotic prefabrication more as a means to efficiently produce locally differentiated composite structures. But we can also turn this inside out and actually use robotic prefabrication as a catalyst to develop new fiber structures and to expand the fabrication solution space as well as the morphological solution space simultaneously. And we're currently trying to do that by developing new and modular and also reconfigurable prefabrication platforms in the course of a multidisciplinary research project together with mechanical engineers and aircraft designers. And instead of a single robot as a fabrication agent, here we are basing those platforms on robot teams, which collaborate. So they work together to create new component typologies and fiber layouts. You can see this here. This was a test where we investigated different kinds of tool-robot fabrication strategies. In this example, two robots are simultaneously winding on this piece in order to finish this component. Another key point of our research is the investigation of alternative material systems. Natural fibers, such as pictured here, have recently gained a lot of significance as an alternative or a more sustainable alternative to carbon and glass fibers. In the construction industry, however, they are almost non-existent. And if we consider the fact that construction is environmentally problematic, it becomes very clear that we also need to look for alternatives here in the material sector. And this is what this kind of material provides. So that's a really good alternative, a more sustainable alternative to carbon and glass fibers. And we recently started to incorporate natural fibers into our colorless filament winding process. And this is the first implementation on an architectural scale of using this new material system. This is a Livmatz pavilion in Freiburg in southern Germany that we completed last year. It's a project that started as a studio project in our iTech master program. And it is basically a load-bearing flax fiber structure that consists of 15 components. All of them are robotically prefabricated exclusively from continuous flax fibers. And the elements are between 4.5 and 5.5 meters long, and each one is around 105 kilograms. I think this is a very promising first implementation of natural fibers in colorless filament winding, and we made the compatibility of fabrication methods and also of our fabrication equipment with natural fibers a key part of our future research. We also learned that transferring knowledge from one material system to another one is not essentially trivial, and it opens up a lot of new and interesting research avenues. So this brings me to the end of my presentation. Thanks a lot for your time, and I'm looking forward to your questions.
Right, thank you very much. Let me see if anyone has any question. You can type in the chat. Maybe I can also invite the previous two speakers to join us at this stage. Yeah, if you're still with us.
Hi, I'm here too.
All right, I think there's one question for Milos.
Mm-hmm.
Regarding it's a question from a student.
Sure.
Yeah, I think she just want to know, oh, sorry, he or she just want to know any tips on software that you can use besides Rhino.
Well, I don't have too many tips aside from Rhino because we kind of use Rhino 100% of the time, and I mean we do explore a lot of modern options like file format options like IFC, and when you look at the IFC, you realize how much of architecture can be done in the notepad. You know, how much architecture can be done with text, because the actual visualization of 3D is somehow less and less important. And when we look at our projects, we often look at the code, we often look at the coordinates, we often look at the text, we don't even look at the 3D visualization. So there is this trend of kind of getting away from 3D. So whatever you use to visualize 3D, it's almost less and less important. Even if you're using some web browser, it's much more important how you handle the data, and we handle the data through programming and code. So So my advice is to use anything that's lightweight. Don't go to these huge software packages. You have to stay lightweight. Rhino is very, very lightweight. There are some other solutions, of course, like Blender and so on, and they all work. They all work. And nowadays they all have all the tools. You just need to, to know what you want. But not a specific advice. Just a Rhino recommendation in general.
All right, thank you. Okay, I don't see a question coming in. I have actually one question for Immanuel. Yeah, if you allow me to ask that, for AI data that you've shown us, can I assume that it's a lot of it is about physical data, or would there be a case where we can actually get AI to learn about emotion or experiences, and can that be used in generating design?
Right. So I had other projects that work with analyzing facial recognition, sentiment analysis, NLP, just that I didn't show them. So it's really how you kind of map or chain these models in the right way. So then the inputs would be, if you decided that the input should be some sentiment analysis that would then map into some 3D geometry, then the AI model is learning that mapping, that function. So the projects that I showed, they are not physical in the sense that, but more digital models, like the 3D models I showed you. Yeah.
Thanks. I'm conscious of the time. Maybe before I end, can I just, because we have a lot of students here, maybe can I hear from each of the speaker, what advice would you give our student? Because what we've seen today, it's something perhaps it's still very new to the student and also in our education here. Yeah. Is there any advice that you can give them? Maybe we can start with Christoph and Hans-Jakob.
All right. Let me think. I think it's a very important question, right? Especially in teaching. I guess a lot of the talks today were about new technologies, and I guess the obvious answer would be to get familiar with everything that is not yet fully embedded within established curricula, right? I think there's always this kind of notion of curiosity where a lot of the interesting things emerge, and I think students and just young people you could even say have a responsibility, right, of really exploring this kind of new aspects. But I think another really important point that I want to stress, and which we are also focusing a lot here in Stuttgart, is that I think these kind of technologies, if we really want to leverage them in a broad scale, right? If we really want to bring them to industry, to a lot of practitioners, then we also need to find ways of how to collaborate and team up and work interdisciplinary on and with these kind of technologies. And I think that also takes a very special mindset, which is sometimes very different from what you would think of as the coder on the computer, right? And I think there's a role for everyone in this kind of process, and I think that's a really important thing also to keep in mind with pushing these kind of things forward.
Yeah, maybe one little thing to add is that, because we had this question before about like the software, and that kind of got me thinking that probably I would not invest too much time to learn like a specific software, but rather to like get some kind of digital literacy almost, and invest in looking at the complexity of architecture and the kind of interrelations also on the level of collaboration, more on an algorithmic level to understand those, to connect those, to kind of reshuffle those and to orchestrate them. I think that's to me more important than to learn a specific programming language or like software package. And because with this knowledge, it's also more flexible because you can apply it on all sorts of softwares and programming languages. So that would kind of be my advice, I think.
Right. How about you, Milos? You're muted. Yeah.
You want a general advice for students, right? That's what.
Yes.
Well, out of all these things that we heard, maybe I think it would be to challenge the status quo, because there is a lot of things that we do in the industry and a lot of things that are taught at university because they are taught before, so it's just reiterated, but no one really questions it. One of the things for me, like the fighting is this 2D, you know, because in our practice, because we work on a large project, there's a huge amount of time wasted just on drawing 2D drawings, and we don't need them, and we really don't need them. Like in most cases, we can really build from 3D to 3D. So there is a lot of inefficiency that is being built in the system. So I always ask students to challenge the status quo and ask why is something done, and if there is a better way to do it, because they will meet with that in their working place after they finish their studies. And if they just shut up and keep doing as it was done before, then nothing will change. So simple examples is that Bloomberg building by Foster that I showed you. And when we generated all the CNC files for all the steel elements that go directly into the machine, then they asked us to produce all those 2D drawings with dimensions, those classical 2D plans for each steel element. And I said, okay, it's going to take like another month to do that. There's like thousands of elements, and we're not going to do them by hand, of course, but we have to do some programming to add some dimensions and so on. Why waste so much time? We already have the CNC files. Just send them to the machine. And then they said, well, we don't know who will manufacture them, and there are some manufacturers that need this kind of old school plans, some that need CNC files. So whenever that is the case, basically try choose to cooperate with those ones that are more efficient, and that's the only way we can progress. Because I'm sad when I see at the university some very old methods being reiterated without any particular reason, and then afterwards we have consequences in the industry. Consequence being not efficient and having less time for doing the creative stuff, because that's what we want at the end.
Right, thanks for that. Lastly, from our academic in SUTD, Prof. Immanuel.
Right, thanks. I think it's very important to be, I mean, this is quite a general statement, important to be open-minded, right? But at the same time, open doesn't mean necessarily following whatsoever that is trending. You should be actually interested in that particular area. So for instance, there are many emerging technology, but if you don't really, but before you decide that you're not going to take on that particular domain or area of research, you should find out a bit more before you decide this is not my thing. But even then, it's worth keeping an open mind. But I think more importantly, at least from my teaching experience in SUTD, is that often we kind of divorce the technical part from the theoretical part, meaning not theory in the sense of the mathematical formulas and framework and whatsoever, but its relation to kind of cultural production. Because after all, as architects, our production is not necessarily just a technical result consequence, but it is part of the societal mood, right? So I think it's always useful. I always find it interesting to cross over, to look at what those guys are doing in AI art, what guys are doing in media studies, what they are talking about, philosophy and aesthetics and all that. What do they mean by, say, I don't know, AI aesthetics? And so there are different strands that suggest different ways of thinking about the same subject. And I don't think it's really our job to be, I mean, architects, I mean, they used to say that architects is supposed to be the top generalist, right? They kind of know many things, but they don't really know like things in depth. So if you take on that kind of thinking, then it is necessary that an architect should also be an intellectual, that also should be technically informed, but not necessarily, unless that's your choice in life. You could specialize in specific areas. But I think since you're students and you're still finding your path, that mindset would be quite useful. To be a bit more like a busybody looking around. Thanks.
All right, thank you. So I suppose the 3 takeaways to be resourceful and be collaborative, challenge the status quo, and lastly, be open-minded and have more I would say, cross-disciplinary mindset, right? Okay, I'm conscious of the time. Let me share my screen for a while to wrap things up. All right, so thank you everyone for joining us today, and we would like to express our gratitude especially to our 4 speakers for taking their valuable time out and joining us from different continents and different time zone as well. So thank you, Dr. Milos Dimcic, Professor Immanuel KOH, Christoph Zechmeister, and Hans-Jakob Wagner. It really opened our eyes to the future of a built environment with kind of limitless kind of possibility. So we also hope that this will give those who are here, and also especially our students taking part in the competition, some inspiration in their design. Before we go, we would like to invite you to visit our website. The link is here in the QR code. You can look at it for more information, especially for the competition brief, as well as today's and last month's webinar video recording. We'll also appreciate it if you can help us spread the word, especially to any students who will be interested to take part in this competition. And with that, I will end today's webinar session. Thank you very much, everyone. Have a good evening if you are joining us in Singapore, and a good day to those in Europe. Thanks for joining us.
Thank you.
Thank you, everyone.
Thank you.
Thanks.
Thank
Bye.
you.
Thanks. Bye-bye.
Bye-bye.
Ciao, ciao.